Hey Elge, quick review of the 9.2 notes on the bell work here. So how do we write this in logarithmic form? If you don't have your note card nearby, I would grab that to remind yourself. So remember that the base number in our exponential form becomes the base in our log. The number on the right side becomes the number in our parentheses, and our power becomes our number on the far side when we put it in this form. Now let's go the other way. Can we go from this logarithmic form into exponential? Remember, the log base becomes the base of our exponent. Our far right side becomes our power, and what was in parentheses becomes the number on the right hand side. And we can double check this because 3 to the 4th does in fact equal 81. All right, last one. If I ask you to evaluate a logarithm, we have to reformat just a little bit. My base becomes my base. My x becomes my power. My parenthesis becomes my far number. What could I put in for x that would bump it down to the bottom? Well, I know that 2 raised to the 3rd power would give me an 8. To put that 8 on the bottom, I'd have to make it negative. So x equals -3. And I've just evaluated that logarithm. So now we're going to take it a little bit further. We're going to talk about some logarithmic properties. So log base b of m times n is going to be the exact same as log base b of m plus log base b of n. Very similar to multiplying numbers where we have x to the m times x to the n, where it becomes x to the m plus n. We're just adding those exponents. Same thing here, we're just adding what's inside those parentheses. When we have log base b of m divided by n, it's the same thing as log base b of m minus log base b of n. And finally, when we have something raised to a power, we're going to bring that power out front and say it's multiplied by log base x of m. So example 1, are these statements true? Why or why not? Well, we've got log base 4 of 4 plus log base 4 of 16. Well, based on our power property that we just talked about here, our final answer should be m times n. Is 4 times 16 64? Yes. Does it end up with the same base that the other two started with? Yes. And I'm just going to say by property 1. All right, our next one, log base 4 of 16 is equal to log base 4 of 4. Is this one true? Yep, based on our property back here it is. So yes, based on property 3. I guess I'll label these for you. 2, 1, 3. And if you wanted to show this in a little bit more detail, you could write them out as their original property. So log base 4 of 4 times 16 is equal to log base 4 of 64. That's one way to show it and see that those are equivalent. Same thing here. I could say log base 4 of 16 is equal to log base 4 of 4 squared. All right, and then the last one. This is a subtraction one, so yes by property 2. And I can say log base 4 of 4, because that's all that really is equal to log base 4 of 16 over 4, or what that left side was originally. All right, example 2. Use log base 12 of 3 equal to 0.4421 and log base 12 of 7 equal to 0.7831 to evaluate each expression. So let's rewrite these based on our properties from above. Log base 12 of 21 can be rewritten as log base 12 of 3 times 7, and we can break those up then into log base 12 of 3 plus log base 12 of 7. I know what those two numbers are because they were given to me. 7831. When I add them together, I get 2252. Next one. How do I break this into something that has this in it? Well, log base 12 of 49 can be written as 7 squared. Remember, based on our third property, we can pull that 2 out to the front and have log base 12 of 7, again, which we know the number for, the formula. So it'd be 2 times 0.7831. And that's going to equal, when I throw it in my calculator over here, 1.5662. Log base 12 of 36. How are we going to rewrite that one? Well, I don't see a 7 involved anywhere. I can't really divide by it or add anything to it. But I can use the log base 3 piece that it gave me to rewrite this log base 12 as 3 times 12. That helps me a little bit because then I can rewrite this as log base 12 of 3 plus log base 12 of 12. And I know the 0.3 part, but also log base 12 of 12, if you put that in your calculator, you're going to find that that is just 1. When the number inside matches the base, those cancel out essentially, and it just becomes the number 1. So if we put this in, we're going to get 0.4421 plus 1, and our final answer is just going to be 1.4421. All right, we're going to find the same thing here with the 1 characteristic. You could add that, I suppose, as a fourth property. I suppose I could have put one on here for you. But log base b of b, when those are the same, they equal 1. All right, so this last one, division, that's going to be our second property. And we're going to say it's the same thing as log base 12 of 7 minus log base 12 of 12. And then we know those two as 0.7831 minus, that's based on our fourth property, it's just 1. Throw that in your calculator, you're going to get 0.2169. All right, almost done here on the first page. There's 2 scenarios to consider when we are solving, and they look like this. We touched a little bit on this yesterday, but we saw that when 2 things have the same base for the log, that their inside terms must be equal. There's no way for log base b of 3 to equal log base b 3 of 2. They have to be the same. And then the other scenario is not really a scenario because we've already talked about it. This is what we did yesterday in 9.2, and it was changing our logarithmic form over to exponential form. And we know that's just b to the y is equal to x. This is just our exponential form. So let's see those 2 scenarios in action a little bit. Let's jump to the back page. Let's solve each of these equations. They look really crazy scary, but I promise you they're not. We just have to use the information that we have from yesterday as well as today. So we know when 2 things have the same base and they're being added, we can multiply those things. So in this case, we're going to have log base 9 of 5 times n plus 1. Notice I'm still leaving it in parentheses because I'm not multiplying the 5 just by the n. I also have to distribute it over to that 1. It's all equal to log base 9 of 6n. Now, based on the fact that these have the same log base 9, I know that whatever is in their parentheses must also be equal. So I'm going to say that and I'm going to distribute in the process here, everything in the first set of parentheses has to be equal to everything in the second set of parentheses. I can solve this pretty easily by subtracting the 5n over, and I just get n equals 5. And if I plug that back in, I'm going to find that it does in fact hold true. Same thing with this next one. Looks really big and scary, but let's break it down. Log base 3 of 6. What's another way to rewrite that? We could rewrite it as log base 3 of 6 squared, and then minus log base 3 of 16 to the 1/4. Notice I'm going to leave the negative in between. I'm not going to take it up with the exponent just because I don't like working with those negative exponents anyway. It's a way for me to make it a little easier on myself. I know that when I have subtraction in the middle, I can divide them. I'm going to simplify in the process here because I know log base 3. 6 squared is just going to be 36. Divided by 16 raised to the 4th is just going to be 2. And it still equals log base 3 of x. And I know because they have the same log and base that I can set these equal. Again, simplifying on my way down, 36 divided by 2 is 18. It's just a matter of looking and recognizing that you don't like the form it's currently in and using those properties that we're going to get more and more comfortable with to put it in a form that we do like. So let's keep looking here. This one's got a few extra steps, but we can't let that scare us off. We have log base 7 of x plus log base 7 of x. When we're adding these two things, remember we're just going to multiply. So we get log base 7 of x squared. I'm not even going to put that as a step. I'm just going to write it here. Minus log base 7 of 3. Because it has that same base, I'm going to combine this into one whole step and just say that it's the first two steps divided by that third one. And it's still going to be equal to log base 7 of 12. Again, I see they have the same log and base, so let's set them equal to each other. X squared over 3 equals 12. Multiply both sides by 3. You get x squared equals 36. Conveniently enough, we can just take the square root, but we have to remember when we take the square root, we get both the plus version and the minus version. However, since we can't have a negative in our log up here, aka when we plug in a -6, we have log base 7 of -6, that negative isn't going to work for us. So our final answer is only going to be the positive version. We cannot have that negative. All right, one more. Log base 10 of z plus log base 10 of z plus 3. Notice a plus becomes a multiplication, so log base 10 of z times z plus 3 equals 1. I can rewrite that 1 eventually, but right now I'm just going to simplify this down a little bit. Sorry, I had to check my notes there. I can make this into z squared plus 3z. But I'm kind of stuck if I leave that as a 1 because I can't solve it other than maybe going into exponent form. But in order to avoid that, I'm going to use my fourth property that we talked about. And that's the one where I can rewrite this as log base 10 of 10. Because as long as these two things match, we know that it equals 1. And since I need a log base 10, all I had to do was write log base 10 and make the number match. Now that these match, I have z squared plus 3z equals 10, which we can then solve by factoring. Minus 10 equals 0. Throw your formula down there. It's going to be positive 5 and negative 2. And I get z equals negative 5 and positive 2. However, I know that I can't put this negative back in. It's kind of one of those things with logarithms that when we get all the way to the bottom here, we just have to remind ourselves that we can't divide by 0 and we can't put negatives in logarithms. It doesn't work. So I know my -5 isn't a viable solution. So therefore, the only answer that I'm going to have is z equals 2. And one last thing before we end, the other great property of logarithms is that you can change the base of your log. So say we couldn't do something like this, where I can't make this a 10, I have to work with some other number. We have something called the change of base here. So you can convert from one base to another. So log base a of x can turn into log base b of x divided by log base b of a. And the typical thing that's going to be put in b is 10, just because that is the typical base in your calculator. So let's use this. Estimate the value of log base 5 of 16. Well, say I can't put that in my calculator because I have one of the simple scientific ones. I can put that in as log 16 divided by log of 5. And my calculator will automatically make these bases the exact same. When it does that, it's just going to divide it for me, and I'm going to get an answer of 1.7227. And that's my final answer. This is one of those formulas, again, if you've been following along with your note card, I would maybe put this one on there as you're studying. All right, let me know if you have any questions.